we can see the output shape is now 2 times 4 times
Hey everyone, welcome to this full 5-hour deep dive into the world of convolutional neural networks. In this
50,257. So this is a shape and this is a corresponding tensor. So where or what do these numbers mean? So we have two input examples, right? So we have 1, 2, and this is why we have this 2 here. And then each input example has 4 tokens. So we have 1, 2, 3, 4. That's why we have the 4 tokens here. But each of these tokens is now represented by a 50,257 dimensional vector. So here, that's where this number comes from. So if I take one of those, so if I, let's say, take the first training example and then take the first token, this should give me a 50,257 dimensional vector. So this would be the embedded token, so 50,257 dimensions. This would be the vector corresponding to the first token, in this case, this one. And it's not necessarily just this one, because inside a GPT model, there's this multi-head masked attention mechanism, which also, which implements, sorry, I almost tipped my glass here, which implements like a concept that combines information from all the tokens. But roughly you can think of it as the token corresponding to the first one here. Okay, so how does it now result in the next word that we want to predict? Because now we have essentially as the output 4 tokens. So for each training example, we have 4 tokens that are 50,257 dimensional, which is like, wow, where does this large number come from and why does it help us in generating the next word? Because like I told you before, LLMs are all about generating the next word. So how do we get from this multi-dimensional concept to just a token, a text token? So how do we get from this to this? And yeah, how it works is a bit complicated, but I think if we go through it step by step, it should hopefully be a bit demystified. So again, taking it from the left-hand side slowly, in the last notebook, when we had some input text, hello, I am a, let's say this is my input text, what we did is we tokenized it. So this is now token IDs. And then this goes into the model. And then we get these 4 rows with 50,257 dimensions each. So this is what we just had above. Now, we are only interested in the next word. We're not really interested in all the 4 output tokens. Because like we talked about before, if I go back a bit, where was it? 1 second. Here. So what I showed you before is when we train or create an LLM, it predicts the tokens shifted by 1. If in blue this is my input, the targets are shifted by 1, right? So in this case, if I have this input, the only new token will be the next one. Here, the last one. Because these, the hard off, they're already contained in the input here, the hard off. So we are interested in the output and then only in the last token of the output. So this means we are only interested in the last row in this case. If I have 4 rows corresponding to my 4 tokens, I'm only interested in my last row here, which corresponds to the new token. Now I mentioned each row will be 50,257 dimensional, and these are the so-called logits. These are just unnormalized scores. Typically it's not necessary for generation, but during training we normalize them to obtain probabilities, and these sum up to 1. And what I do then with these probabilities is I look for the largest probability in this probability tensor. So again, I go from token IDs to token embeddings, and then based on the output for the token embeddings, the last token, I look for the largest value. In this case, let's say it's this value here. And this value corresponds to position, let's say 257. I dotted out a few because otherwise it would be too long. And so what I'm doing here is I'm looking for the largest value in the last token, and then I get the token ID, and then I can use my tokenizer decode to decode this token ID back into a word or token string. So in this case, hello, I am is my input, and then I get this A, which is the next token, and I add this back to my input, and then I do another round where now the model gets the original tokens plus a new token, and then again it generates the next one, and so forth. So this is how we get the LLM to generate always the next word. This is how we get this text essentially, that we start with this one, the blue one, we generate this A, and this A gets added as input again, and then the next word is, let's say, model, and we add this model here back here, take this whole thing as input, generate the next one, and so forth until we have the full text. So it's really just generating one word at a time that we keep appending back as the input. This is sometimes also called as teacher forcing, but I don't like this term. So it's basically just adding the token back as the input. And here's a simple function without bells and whistles to implement this concept. So we iterate over the number of tokens we want to generate. So let's call this max new tokens. And then we get the indices. So here I'm truncating them a bit because, like I mentioned, LLMs can only support up to a certain context size, let's say 1024. In case I have more text than my LLM supports, I would truncate this. But this is actually, for our simple case, not necessary because we have a very small context. Okay, so what I do then is I create these logits. The logits are these values here. They're just called logits. And I get the last value here. The -1 is the last position. So the columns are the 50,000 dimensions, and here the dimensions, the rows are 1, 2, 3, 4. I'm getting the last one, -1 in index in NumPy and PyTorch is the last one. I apply my softmax function, which gives me these probabilities here. And then I look for the largest probability. Specifically, I look for the position where the largest probability is. So in this case, let's say this is position 257. And this will become then my new generated token ID. And then I concatenate the original here, the original indices, with this next token essentially. And this is essentially how we generate one word or one token at a time. So here's the whole concept visualized again. We have some input, generate the next token, append it back, generate the next token, append it back, generate the next token, and append it back. And this is how it works, how an LLM generates one token at a time. And so for the exercise, I have not shown you how to use this function. It shouldn't be too complicated, I hope. I have some instructions. I would say maybe pause the video and try it yourself. See if you can use the previous function that I showed you to generate some text. So maybe pause the video here, and I will then continue. So for me, it's been a time sometimes since I made this notebook, but let's see if I can do this off the top of my head. So the question is essentially how we use this function that we implemented. So let's do some text, some example text, and then we first encode it. So we get the token IDs. So we have the encoded text. Let's call it like this, and then we have the tokenizer encode text. Should work. So we have 3 tokens in this case, and I mentioned here. So we need first to apply the torch tensor to convert this into a tensor. Can do it right here. So this is now a torch tensor. One thing is our network expects a batch size. So the way we coded it is it wants a batch size. We can see that here that, where was it? Here we have 2 batches. So we have to add this batch dimension. In PyTorch, one way to do it is using the unsqueeze. Oops. Yes, that's right. We use the unsqueeze, which adds a new dimension at the 0 position. So let's see how I can show it to you. So if I have just a one-dimensional tensor with 3 elements, I can actually also use, I think, random. So I have one dimension. I can then do encoded text and then do unsqueeze and first dimension. So this should be now adding this new dimension. So now I have a 2-dimensional tensor like this, and we have to maybe assign it to a variable. Let's call this batch input, and then we can use our text generation function. So let's use that, just copying it here. So we can just call it model. The indices are the batch inputs. Let's say we want to generate 10 new tokens, and the context size, our model has context size of 1024. Let's see what happens. Not defined. Okay, let's try this again. Batch input is not defined. Did I not?
What are design patterns? The idea of category proven patterns was introduced in the field of architecture by Christopher Life. Each pattern describes a problem which occurs over and over in our environment and describes the core of the solution of the problem without doing it the same way. Each solution is stated in such way it gives a field essential relationship between solve the problem, but in a very general, the abstract way. You should solve the problem for yourself in your own way by adapting it for your preference, the local condition, and the place where you're making it. For example, a couple of patterns incorporate every human detail where the building of okay. Data representation, whatever. It's like it's completely being a doctor. It's like, bro, working a job is completely fake. It's like, get that shit out of it. It's like, I'm a doctor, I'm an engineer. You're a slave. You're a slave. I'm a slave. You're all slaving in my life. There's no better way to put it. It's like, now I'm gonna kill you. It's like, oh, slave. That's exactly what a slave would say, actually. Remember, actually, you're not a slave. It's like, okay, slave. Shut up. No,
So hi everyone. So yeah, like I've been taking like a long break from streaming, but I can sort of at this point, I think, pretty confidently say that the regular
data engineering described. What is data engineering? Data engineering defined. Data engineering life cycle, evolution of data engineering, data science. Okay, data engineering life cycle. More like the DevOps side of things, storage, ingestion, serving data. Major undercurrent across data engineering life, security, data ops, data architecture, choosing technologies across. Okay. Data ingestion. What is ingestion? Okay. Ingestion, SSH. Oh, web scraping, data ops, all of that. data representation design patterns. Problem representation. Okay, what are some data?
I'm just double checking. All right, so we're live. Hello, everyone. Welcome to our GDG Seattle meetup tonight. GDG Seattle is a fast-growing community with over 7,000 members, and we are an inclusive community where everyone is welcome to learn, practice, and share Google technology, services, and platforms. Our motto is be excellent to each other. If you see or experience anything different, please contact GDG Seattle.
There are two things that we should know about: precision and recall. Precision.
Hit record.
Long business. Long business.
My favorite design pattern. My favorite design pattern, right, as I think everyone is the thing that used to be super hard until the pattern came along and it made it super easy. Okay? And the thing that used to be super hard for me, because I've been doing ML for a long time, was this idea of stateless serving pattern. Right?
Thank you so much, everyone, for joining this Notebook Club.
There are two things.
Whenever I'm making
So your company has 500.
Today, we'll explore prompt engineering and understand why it's such an essential skill for AI engineers. Traditionally, a user provides a query, and this query is called a prompt. It is passed to the LLM, which processes it and generates an output. Prompt engineering improves this process by crafting clear, effective instructions and adding them to the user's query before sending it to the LLM. The instruction defines rules to follow, the communication style, the purpose, and the overall goal. This greatly improves the quality of the output produced by the LLM. So we can think of prompt engineering as an intermediate step before sending the user's query to the LLM. In this step, we apply various techniques to enhance the query with clear and effective instructions. So what are the main techniques used in prompt engineering? Let's go over the most important ones. 1. Few-shot prompting. In few-shot prompting, we include a few input-output examples in the prompt to guide the LLM's behavior and help it understand the desired pattern. For example, if we want to use an LLM as an English to French translator, instead of just sending the query, where is the train station, we can first provide a few English to French translation examples and include them in the prompt as part of the instruction. This way, the LLM can follow the same format, tone, and style we desire by following the format of provided examples. 2. Zero-shot prompting. In zero-shot prompting, we only provide an instruction for the translation task without including any specific examples. For example, we can give an instruction like translate the following sentence into French. This makes the task clear and helps the language model understand exactly what to do. 3. Chain of thought prompting. In this technique, we ask the model to reason step by step before giving the final answer. In its few-shot setup, we encourage a step-by-step reasoning by including examples that demonstrate this reasoning process. In a zero-shot setup, we ask the model just to reason step by step before answering. This often improves the quality of the LLM's output. 4. Role-specific prompting. In role-specific prompting, we instruct the model to take on a specific role or persona. For example, we can instruct the model by saying, "You are a financial advisor." This helps the LLM generate more accurate and context-appropriate responses. 5. Prompt hierarchy. In prompt hierarchy, we establish different levels of authority within the instructions. A typical setup includes a system message where hidden instructions define the model's behavior, guardrails, and high-level goals. This instruction is known as the system prompt. A developer prompt contains instructions from the application developer that define formatting roles and customize the LLM's behavior. And finally, a user prompt, which is just the user's direct input or question. Together, these three levels form the complete prompt that is sent to the LLM. While these are the most common prompt engineering techniques, there are many others as well, such as negative prompting, where we include do not instructions that specify what the model should avoid doing. Iterative prompting, which relies on trial and error to refine and discover the most effective instruction. And prompt chaining, where we break a complex task into smaller, more manageable steps and guide the model through them in sequence. For example, instead of directly asking an LLM to determine if a product is healthy from an image of its ingredients, we can first ask the LLM to extract the text from the image and then decide if the product is healthy. What are the principles and best practices? Here are some key principles and best practices to keep in mind when designing your prompts. 1. Start simple. Begin with straightforward prompts, then gradually move to more complex ones. For example, start with a simple request like summarize this article. Once that works well, expand it to something more detailed, such as summarize this article in 2 sentences for a startup founder. 2. Break down tasks. Divide complex tasks into smaller manageable steps. For example, instead of asking write a full research proposal on education, most modern AI products are built from the same set of core ideas. In the next 7 minutes, I'll walk through 9 concepts you will see repeatedly across real-world AI systems. 1. Tokenization. Neural networks like LLMs cannot work with raw text directly. A tokenizer breaks text into smaller units called tokens and maps each token to an integer ID, so the model can take the sequence as input instead of raw text. The most common algorithm is byte pair encoding, or BPE. BPE starts from small units, often bytes or characters, and repeatedly merges the most frequent adjacent pairs to form new tokens. Over time, common fragments like ing or tion become single tokens, so words like walking might be split as walk plus ing. 2. Text decoding. An LLM simply outputs a probability distribution over the vocabulary for the next token. A decoding algorithm chooses one token from that distribution, appends it to the sequence, and repeats the process to produce a full response. The simplest text decoding approach is greedy decoding, which always picks the most likely next token. It can work well for deterministic tasks, but not for tasks requiring creativity. Sampling-based methods add controlled randomness to improve diversity. For example, top P sampling draws the next token from the smallest set of tokens whose probabilities sum to P, then samples from that set. 3. Prompt engineering. Vague prompts usually lead to vague answers. Prompt engineering is the practice of shaping instructions and context to steer a model's behavior without changing its weights. A strong prompt clearly states the task, key constraints, and the expected output format. One common technique is few-shot prompting, where you include a handful of examples so the model imitates the desired style and structure. Another is chain-of-thought prompting, which you ask for step-by-step reasoning. COT prompting can improve performance on problems that require multi-step logic like math and coding. Prompt engineering is widely used because it is fast to iterate on and inexpensive compared to training or fine-tuning a model. 4. Multi-step AI agents. An LLM on its own only generates text. It cannot take actions like browsing the web, checking the weather, or running code. Multi-step agents wrap an LLM in a loop with access to tools and memory, so it can plan what to do next, call external tools, and use the results to decide the next step. The agent repeats this cycle until it reaches the goal, runs out of a budget, or determines it cannot make further progress. 5. Retrieval augmented generation. A plain LLM answers using only what is stored in its weights, so it can be wrong or outdated on recent events or changing company policies. RAG pairs an LLM with a retrieval system connected to a knowledge store. When you ask a question, the retriever first pulls relevant passages from sources like PDFs, docs, or a database, then the LLM uses those passages to write the answer. This grounds the response in external evidence instead of relying only on the model's memory. 6. Reinforcement learning from human feedback. The initial launch of ChatGPT succeeded in large because of the RLHF stage. RLHF is a reinforcement learning approach where the model practices by generating multiple candidate responses. A separate reward model scores them, and the training algorithm updates the model's weights, so higher scoring responses become more likely. Over time, this pushes the model toward outputs that people consistently rate as more helpful, clear, and safe, not just outputs that are statistically likely. RLHF aligns an LLM with human preferences, mainly because of how the reward model is trained. The reward model learns directly from human feedback, usually from pairs of model responses to the same prompt where annotators pick the one they prefer. By learning these preference patterns, the reward model becomes a proxy for what humans tend to want, and reinforcement learning uses that signal to steer the LLM toward responses that score higher on that proxy. 7. Variational autoencoder. A VAE is a generative modeling approach that learns a probability distribution of data. A VAE consists of 2 neural networks, an encoder and a decoder. The encoder maps the input into a low-dimensional latent representation, while the decoder maps the latent vector back to the original input space. Training optimizes a reconstruction objective, so the decoded output stays close to the original input. After training, new data can be generated by sampling a point from the latent space and decoding it. In modern text-to-image and text-to-video systems like OpenAI's Sora, a VAE is often used as a latent compressor, allowing the downstream model to operate more efficiently in a smaller space. 8. Diffusion models. Diffusion models generate data by learning to reverse a gradual noising process. During training, you take real samples like images, add noise over many time steps, and train a model to predict the noise given the noisy input, the time step, and optional conditioning such as text. At inference time, you start from pure noise and repeatedly apply the learned denoising step to move toward a clean sample. 9. Low-rank adaptation. Large models like LLMs and text-to-image systems are general purpose. They handle broad everyday tasks well, but often struggle in specialized domains. LoRA is an efficient fine-tuning method that adapts a pre-trained model without updating all of its parameters. It keeps the original linear layer weights frozen and adds 2 small low-rank trainable matrices, so the model can learn domain-specific adjustments with far fewer new parameters. With this foundation, you should find reading future AI designs and articles much easier.
The world of open source AI has exploded, giving
Most modern AI products are built from the same set of core ideas.
The world of open source AI has exploded, giving us freedom and control over AI projects. Gone are the days when AI development was locked behind proprietary walls. Open source breaks down these barriers, and let us experiment without huge upfront costs. So what does this open source AI stack look like in practice? Let's break it down, starting with the front end, the gateway to our AI applications. For scalable apps, frameworks like Next.js and SvelteKit shine with their streaming capabilities. It's crucial for showing AI responses as they are generated. For rapid prototyping, tools like Streamlit and Gradio let us build interactive interfaces in pure Python, though we might need something more robust as our apps grow more complex. Let's talk about the data layer, where we connect our AI models with our specific data, whether it's documents, product catalogs, or customer records. A key concept here is RAG, Retrieval Augmented Generation. Instead of fine-tuning models on our data, RAG dynamically pulls relevant context during inference. We first convert our documents into vectors using embedding models, store them in a vector database, and then at query time, we retrieve the most similar chunks and inject them into the model's context window. This gives us up-to-date responses and precise control over our AI's knowledge base. For making sense of our vector spaces, Nomic Atlas helps us visualize and debug our embeddings. When we need to handle documents, Lama Index helps us build robust processing pipelines, from splitting text into meaningful chunks to generating embeddings. For handling diverse file formats, from PDFs to Excel files, Apache Tika handles the heavy lifting of content extraction and metadata parsing. For multimodal search, Gina AI let us work with text, images, and other data types in a unified vector space, with built-in support for cross-model querying. Now for the backend, Fast API gives us that solid API foundation we need, with WebSocket support built right in, great for streaming our AI responses in real time. When we need to connect multiple AI operations, LangChain helps us build those complex workflows while keeping everything in clean, maintainable Python. Then there's Metaflow, which let us write ML pipelines as straightforward Python code, while handling the complex parts like data versioning and orchestration automatically. And we can scale from our laptop to the cloud with minimal changes. For working with models, we've got some great options. Ollama makes local development on smaller models easy, almost like we're working with Docker before AI. Then there's the Hugging Face ecosystem, opening up a world of community models we can access programmatically. For storage, we've got options that fit different scales. If we're already using Postgres, pgvector gives us vector search capabilities right in our existing database. When we need to go bigger, Milvus and WeVA are purpose-built for this, with WeVA standing out for its hybrid search combining vector and keyword approaches. The LLM landscape is especially dynamic right now. Models like Mistral and DeepSeek are pushing what's possible with open-weight models, with tools like Llama.cpp with
Most modern AI products are built from the same set of core ideas. In the next 7 minutes, I'll walk through 9 concepts you will see repeatedly across real-world AI systems. 1. Tokenization. Neural networks like LLMs cannot work with raw text directly. A tokenizer breaks text into smaller units called tokens and maps each token to an integer ID, so the model can take the
Design patterns are spoon-fed material for brainless programmers incapable of independent thought, who will be resolved to producing code as mediocre as the design patterns they use to create it. A quote from Krista Erickson, who is the now former director of technology at Sony Santa Monica, and if you haven't read it, the author of Real-Time Collision Detection.
Python has much stronger support for.
This is the most hardcore machine learning model I've ever built. Based on the 2016 research paper LipNet, which was originally developed by researchers from DeepMind.
Action as fraudulent. In this case, it's really important to know why the model thinks.
Fuck you.
of PostgreSQL over MySQL. Knowing the difference between SQL and NoSQL is table stakes, and it simply does not cut it. Understanding ACID and CAP theorem is the bare bones expectations in 2025 for every competent entry-level engineer. But the engineers who get ahead in this market, they understand the low-level architecture that makes PostgreSQL special as a database management system. If you don't know these concepts, then you should consider watching this video, where I'm going to break down how PostgreSQL works, its architecture, and some of its nifty details around multi-version concurrency control and 99% of developers expectations in 2025 for every competent entry-level engineer. But the engineers who get ahead in this market, they understand the low-level architecture that makes PostgreSQL special as a database management system. If you don't know these concepts, then you should consider watching this video, where I'm going to break down how PostgreSQL works, its architecture, and some of its nifty details around multi-version concurrency control and write-ahead logging. This is the knowledge that will make you stand out as an engineer. Let's get started. PostgreSQL is a relational database system. It stores structured data and lets you query and manipulate it using SQL. But it's not just a data store. It's a transactional, concurrent, extensible data engine built to guarantee correctness, consistency, and durability at scale. At its heart, PostgreSQL implements the ACID model. Atomicity, every transaction is all or nothing. Consistency, data always moves from one valid state to another. Isolation, concurrent transactions do not interfere. And durability, once a transaction commits, it will not be lost, even after crashes. PostgreSQL's entire architecture, from memory management to logging, is designed around enforcing these four principles efficiently. But actually, PostgreSQL is an object relational database. This means it combines traditional relational database features like tables, rows, foreign keys with object-oriented concepts like custom data types, functions, and inheritance. You can define complex types, store arrays, JSON, or geometric objects, and even attach methods or operators to them. This flexibility allows PostgreSQL to handle both standard relational workloads and more advanced semi-structured data patterns. Now let's look into the architecture of PostgreSQL. PostgreSQL follows a client-server model. The server, or postmaster, manages data, and clients such as applications, APIs, or the PSQL CLI connect via TCP. When you start PostgreSQL, it spawns several background processes. Back-end processes are one per active connection which execute the SQL statements. Background workers handle caching, vacuuming, and checkpointing, which we'll get to later. And the writer and write-ahead logging processes manage persistence and recovery. We'll touch on this as well. Underneath, all data is stored on disk in a directory called the data cluster, which contains databases, schemas, tables, indexes, and write-ahead logging logs. PostgreSQL separates logic, such as how queries are executed, from storage, which is how data lives on disk. It's a design that gives it both flexibility and fault tolerance. Now onto the data storage model. Every table in PostgreSQL is stored as one or more heap files on disk. These heap files are collections of fixed-sized
Let's say your company has an employee handbook that covers policies like time off requests, dress code, and equipment news. Employees might ask questions like, can I wear jeans in the office? Or can I request time off on a holiday? Or can I bring my company laptop home for the weekend? While these are common questions that people would typically ask, building a database around this requirement can be a little bit tricky. In a conventional approach where data is stored in a structured database like SQL, you typically need to do some amount of similarity search like select all from documents where content like holiday or time off with the ampersand around it. And to expand your result set, you might even increase the scope by dropping a few characters like this and removing spaces between time and off like this. However, the drawback to this approach is that it puts the onus on the person searching for the data to get the search term formatted correctly. But what if there was a different way to store the data? What if instead of storing them by the value, we store the meaning of the words? This way, when you search the database by sending the question itself, can I request a time off on a holiday instead of the SQL query? So based on the meaning of the words containing the question, the database returns only relevant data back. This is a spirit of what vector databases try to address, storing data by the embedding. So essentially, instead of searching by value, we can now search by meaning. While conceptually, this might seem a little bit straightforward, there's a bit of an overhead in setting this up. And you might be asking, well, can we just throw the employee handbook document into the database like we would in SQL database? Not quite, and here's why. With SQL databases, the burden is actually put on the user searching for the data that's stored in the structured database, but with vector databases, the burden is put on you who is actually setting up the database, since you are trying to make it easier for someone searching for the data that's inside it. And you can imagine why a method like this is becoming extremely popular when paired with the large language models in AI, since you don't have to train the LLM separately on how to actually search your database. Instead, the LLM can freely search based on meaning and have the confidence that your database will million.
What is a
Fuck you. Encode is decode.
If you're doing a degree in physics, math, or engineering, learning SciPy is essential. Suppose you go through some big, long mathematical derivation and you get a differential equation, for example, and maybe you can't solve it. Well, that's what computers are for, and that's what SciPy allows you to do. Today we're going to look at things like interpolation of data. We're going to look at fitting data to functions. We're also going to look at things like integration and differentiation. We're going to solve complicated ordinary differential equations that you can't solve by hand. We'll delve into the linear algebra library of SciPy, which can deal with problems that involve very large matrices by using clever techniques to store the data. Finally, we'll look at a little bit of the statistics of SciPy as well, for things like generating random numbers. Suppose you have your own.
NumPy and SciPy are two essential libraries in the Python programming ecosystem. And while both are used for math-type things, there are both fundamental differences and areas of overlap between